Okay. I want to welcome everyone. Thank you for joining today's webinar, Building Robust, Smarter Industrial Control Systems, co-hosted by ISA and Ultra Electronics. My name is Michaela Cooper. I'm with ISA, and I'll be hosting today's webinar. Before we get started, I'd like to review a few housekeeping items and let you know how you can participate in today's session. First, in regards to the question and answer session, we have a Q&A session towards the end of this webinar. To submit your questions, just simply type them into the Q&A box on the right-hand side of your screen. I'll ask that you do not use the chat toolbox for the Q&A session. If you have any sort of miscellaneous questions or you're experiencing any technical difficulties, you can submit those into the chat toolbox for me, the host. And unfortunately, with this large amount of pre-registrants, we cannot open the phones for questions. If we do not get a chance to respond to your question, or if you'd like to discuss a topic in more detail with the presenter, feel free to contact them directly, and their contact information will be given at the end of the webinar. Second, for those of you who just joined, please make sure you are on mute. If you would like to see the phone and audio broadcast connection instructions again, please refer to the confirmation email I sent to you today. Or if you go to the top left-hand side of your WebEx screen, you'll see a tab labeled Event Info, and some of those connection instructions are included there as well. Additionally, once this webinar closes, a survey should pop up in your browser. You'll want to take just a few minutes to fill out the survey and tell us about your experience at today's webinar. Okay, I believe that takes care of all of our housekeeping matters. We can go ahead and get started. I'd like for our presenters to take it from here.
Thanks very much, Michaela. Hi, everybody. My name is Alex Tata. I'm the Technical Director over at Ultra Electronics 3TI. My background is I'm a native civilian cyber advisor for critical infrastructure. I've done a lot of work in this area from aviation to power systems and building automation systems, but have a strong background and interest in cybersecurity.
Hi, my name is Adam Crane. I'm primarily a software engineer. Most of my time has kind of been spent working on products and systems in electric power. Over the last 3 or 4 years, I've increasingly been spending kind of more time doing testing and validation with my researcher hat on, and that's included a lot of kind of responsible disclosure and unsolicited testing to DHS and vendors. So I'm here today to kind of provide a little bit of perspective from researcher slash hacker.
That's great. Thank you very much, Adam. So just before we get started, I'm sure a lot of you have no idea who Ultra Electronics is, or even specifically 3TI. Ultra Electronics is about a $1.2 billion company based in the UK and in the US. We do a lot of work, including government work, critical infrastructure work, but deploying out solutions, really trying to provide smart and robust critical infrastructure solutions, and exactly what we'll be talking about today. So a little bit more about who we are, what we're going to be talking about today. And the first thing is we're going to talk a little bit about ICS, some of the assumptions that go into it, mainly because the way you do security is by essentially challenging all of your assumptions. You've designed it a certain way. You need to find out really exactly how it does work, and then mitigate those issues which are outside of how you want them to work. Specifically, we're going to talk about making it more robust. We're going to talk about making an ICS system more smart and what we mean by that, and then ultimately tie those together to create a more resilient system, and then actually how you can go about solving it for yourselves. So we'll tell you a lot of what the problems are, but we'll hopefully end on a high note and tell you how you can solve your problems. So a little bit for those who are unfamiliar with how traditional ICS architectures are. We're very used to thinking about industrial control systems as being everything in the top right-hand corner. That's all the industrial processes. That's big machinery connected together via PLCs, but not really us understanding that behind those big pieces of machinery and all of those controllers sits a hierarchy of other cyber infrastructure, specifically in the process control network, or all of the HMIs, the big server rooms, the big control rooms that operators set up to see sensors and instruct things going on. But behind that is also a support network where information is stored, and also information is distributed out to external networks. Primarily, if you think of a power station, in addition to generating electricity, it also needs to report back to the EPA or environmental agencies saying how much CO2 I've produced or how much electricity I've produced. There's a whole back office enterprise system coming up. So while I say there is a large degree of PCs and IT network infrastructure, and in many of those infrastructures we have some good solutions in place, it's really the second half of that. It's all the embedded systems down towards the control end that we really want to speak about today, because this is where cybersecurity is lacking within industrial control systems. This is where some of the design assumptions are really being challenged when it comes to security. So what do we mean when we say design assumptions? Primarily, everyone is who they say they are. This is one of the most important ones. That is, down at the control network, we just assume that the devices plugged in, the devices communicating, are who they say they are. Why? Because we physically put them there. But we have no way to really validate that that is the case. We have no ability to say, this is definitely my PLC, it's not somebody else's PLC, or even it's not a Raspberry Pi or a laptop plugged into the network pretending to be a PLC. Same thing as you can see the next layer up, the maintenance laptop. We have frequently engineers come on site to fix issues and they plug their own laptop in. And so you just assume that the laptop they're plugging in is completely owned and maintained by them. All the software is theirs, and everything transmitting over that is exactly who they say they are. In reality, we just cannot make that assumption. There is nothing backing up that assumption. What is said is what is heard. This is quite important because within an industrial control system and many industrial control protocols, we have no method of protecting the communications. These are normally built off of previous generation systems, which are all used to being a serial network. The idea is if I flip a switch in a control network, I have a hardwired connection directly from that switch all the way out to the controller, which will implement an action. So actually, what is the action of me flipping a switch is directly proportional to the voltage going over the wire, which causes something to happen. Now we strip that away and we've added in IP networks. We've taken the same protocol and just thrown it over the IP network. We have no longer that same assumption that an action from a controller is actually what is received at the far end. And this is, we'll talk about a bit later with Stuxnet, exactly what happened. Because the information coming over the network isn't exactly what they thought it was, nor what was being displayed to the user exactly what was actually going on. So we can't trust who's speaking. We can't necessarily trust what everybody is saying. And that the errors that we're trying to detect and recover from are those introduced by noise. So we just assume that if a packet of information comes in with no errors, or if there are errors, those have really been introduced by noise, and that there's no intentionally bad actions. Which leads us on to the next one, the fact that events are accidental, not intentional. That's how we've designed the safety systems of our networks. That's how we've designed the safety systems of our ICS. The idea being that there's not necessarily a malicious actor coming in and intentionally doing wrong, which is difficult when you talk about security because that's exactly what malware is trying to do. They're intentionally causing incidents. They're intentionally causing something outside of the normal. That's pretty much the definition of security. So when we talk about design assumption for an ICS, you can't necessarily make the case that all events will only be accidental or safe. They could be unintentional or intentionally bad actions. We also talk about availability being paramount. That is, when I need to make an action or I need to see what's going on, absolutely availability is key. We talk a lot in security about confidentiality, integrity, and availability. And we always say that within industrial control systems, nobody really cares about the confidentiality of information. It's just not secret, but we really, really, really care about the availability. We need to be able to turn things on and off. And as we'll show later, availability is a good thing from a safety point of view, but may not necessarily be your best friend when it comes to a security point of view. And finally, reliability is success. We all know this. When you do your job, the reliability of the system stays up, stays high. You hit your key performance indicators. You produce, you manufacture your process, and everybody's kept happy. So reliability is the key indicator of a job well done. And we'll show that actually in an ICS system, reliability is very hard to do, and actually an intentional action can hit the reliability of the system. So what I'd like to do now is hand it over to Adam to provide us with a bit of insight from a security researcher's perspective as to these assumptions. Are they really valid in reality?
Thanks, Alex. Hackers and security researchers, and I tend to kind of use those terms interchangeably, tend to kind of view knowledge as power. They kind of love the challenge of figuring out how a complex system works and then kind of analyzing that system for hidden assumptions. Traditionally, it's been kind of hard for researchers and hackers to kind of fully understand how industrial control systems work because not all the information is public. A lot of it is tribal knowledge. It's really hard to get a hold of the equipment, but that's kind of changing. A lot more of the information is becoming available, even kind of at the mainstream security conferences. We're starting to see things like industrial control system villages pop up, where people are actually given the opportunity to play with real control systems hardware. So I think that is kind of changing within the community right now. And then the intentions of these folks is usually not nefarious. They're not out to get you. If you get contacted by a researcher, if you're a vendor, or maybe if you're an asset owner and somebody contacts you and says they found a public IP on the internet, if you hear from those people, that's generally a good sign. They're usually there to help you and provide you information. So, sending people cease and desist letters is generally an uphill battle against human curiosity. So I think the right way to view hackers and researchers is kind of an unsolicited external, QA department. And we can go on to the next slide here. So hackers like to challenge assumptions. And when they're first analyzing a system, they're definitely going to look for those hidden assumptions. And when you have something you believe to be true and you didn't prepare for it or put any compensating controls into a system, and then either by accident or because of a nefarious actor, that false assumption is exposed, that's when scary things tend to happen. So those types of false assumptions could include things like, do all the vendors in the system for a particular protocol, do the protocols actually speak the same dialect to the protocol? I can't count on one hand the number of times I've heard stories on various control system message lists where vendor A talks to vendor B with, OPC or whatever the protocol happens to be, and vendor B's system, just tips over because it's never seen that kind of message before. And that's the kind of the difference between reliability and resilience that we'll talk about later in the presentation. Other assumptions can include where are my egress and egress points, where does information flow into my system, does anyone ever plug in authorized device and media, can a controller actually tell who's controlling it? There are still people that think that CRC checks, like Alex was saying, will protect you from somebody who's intentionally sending you bad data versus just protecting you from, environmental noise. And then can your system actually tell the difference between an equipment failure and a cyber attack? And that's kind of the classic Stuxnet example. A lot of the attacks that we've seen or we hear about, the attacker wants to kind of maybe do damage over a long period of time instead of one classic thing or one catastrophic event. So being able to tell the difference between just kind of intermittent failure and actual attack becomes really important. So I'll turn it back over to Alex now.
Thank you very much, Adam. So really we want to talk about is two major things coming off the back of that. One of which is, can we, we need to control, can we trust who's doing the talking? Can we make sure that the system is robust? And then secondly, can we trust what is being said? So in reality, to begin with, we want to talk about fragility versus robustness. Now, This is quite a common one. This is what I hear a lot about whenever we go in and try and talk about security for ICSs. The first thing is, my ICS is very fragile, you can't touch it. If you plug something in, you could bring the whole thing down. That is, don't touch it, I could lose my job. If the system breaks, if something happens, we stop producing, reliability goes down, and I get my job, and I lose my job. So nobody can touch the control environment. Well, this is pretty much the definition of fragility. The whole idea here is, if you as a legitimate user can't touch your system in case it falls down, well then it's very easy for malicious users to do anything and cause a big impact. So by the very nature of it being fragile, this is actually a big security concern, because at some point, some bad piece of malware, some bad piece of equipment, be it a laptop, or even just accidentally, nothing nefarious, just somebody plugging something in at the wrong place or plugging a controller in the wrong way around, could have a severe impact on your reliability. A robust system would say, go ahead, plug in whatever you want. It can't really do anything. I'm pretty robust. You try and hit me, I'm not going to fall over. So that comes to the second point of really what a fragile system is, and that is a user could unintentionally impact my system. One small change, one small action shouldn't have an outsized impact. You shouldn't be able to cause a big issue by a small action. And so a robust system says, you know what, we can't handle everybody doing everything malicious to us, but we should be able to withstand a few accidental knocks, bangs, a few things being plugged in the wrong way around, a few devices being plugged in when they shouldn't be. We should have a robust system, should be able to handle all of these little robust security incidents. And then finally, a fragile system is one in which a malware on the PC could seriously damage the system. In a robust system, on the other hand, malware may be disruptive, but it won't be damaging. And the difference there is malware may be able to get on the system, may be able to cause interference, may be able to manipulate what's going on, but it shouldn't ever cause significant damage. A bad actor shouldn't be able to do something very dangerous. And actually, this happens more than you may think. And it's a little more scary than you actually might imagine. So I'd like to bring Adam in to actually tell us a little bit more about what he has seen in reality.
So my company led a kind of big research campaign in 2013, 2014, and we tested distributed network protocol, that's DNP3 stacks, from over 20 vendors. And we found that about 90% of the products we tested had easily kind of exploitable defects. You know, these defects range from simply the software crashing to being able to paralyze the SCADA master in infinite loops so it couldn't talk to kind of any of the substations in that region, all the way to issues where someone with more of a low-level programming background than me could probably run code against the SCADA master. And that shook up a lot of assumptions. You know, folks on the technical committee for DNP3 and people within the industry really assumed that that software would be more resilient to someone actually testing it in that way. You know, another example that I found really interesting was with Havix. And there's a lot more to the Havix story than this, but if you look in the actual ICS Cert bulletin to Havix, they said it was important to note that ICS testing has determined that the Havix payload has caused multiple common OPC platforms to intermittently crash. And this wasn't a feature of Havix. Havix wasn't trying to intentionally cause damage by crashing things. It was just doing reconnaissance by scanning. So the malware was could intermittently have tipped over communications to things even though it wasn't. So that's a great example of things that are kind of fragile by nature. And you know, these are the kinds of things that QA engineers at large vendors will be looking for when they're kind of doing quality control on products. They'll enter all kinds of things into the wrong fields. They'll challenge the assumptions about the way the system should be used. Next slide, please. And this often raises the discussion between asset owners and vendors for whose responsibility is to secure systems. Frequently, when I have kind of like disclosed bugs to a vendor on behalf of an asset owner, I always witness the discussion where the engineer or the company is saying to the vendor, you know, you sold us something with bugs, we'd like this fixed. And the vendor says, well, this was within the control network, it's a trusted network, you should really just control your network. So who's really responsible for shoring up some of the fragility that we have in these systems. And I think the truth kind of lies somewhere in the middle. Study after study shows that it's much, much cheaper to fix bugs prior to deployment for everybody involved, because yes, maybe the asset owner has to pay a little more for those components for the testing, but because they have to deploy patches less frequently and because that software will be more reliable just in normal communications, they can kind of save money in the long run. So I completely think that it's vendors' responsibility to do more upfront testing, but asset owners have to understand that there's no such thing as perfect software. There's no silver bullet on the horizon to ensure that anyone can deliver perfect software, and we need compensating controls that will allow for the unexpected when it comes to bugs in software. So all we can really ask for is low defect rate software or high quality software.
Cool. Thank you very much, Adam. Well, we'd like everybody to wake up a little bit and take part in a little bit of a poll for us, because, as we've mentioned, a lot of people assume that industrial control systems are reliable but not necessarily robust. So we'd like to just throw it out there and see, of your systems or the systems that you've interacted with, how many of them, are your systems robust? Have you gone out and tested it? Is your IT department allowed to make changes on the industrial control system? Or is it very fragile? Are you assuming that basically nobody can touch anything in case it all falls over? Is there a culture of fragility or really a culture of robustness with your industrial control systems? So I think we're going to give people about 30 seconds just to quickly throw in their own responses. Okay, so I think we'll probably close the polling in about 5 seconds and move on, have a look at the results and see what they tell us. Okay, so the poll has ended and we're just waiting to see the results come in. It should be here in a few seconds. All right, so as you can see, hopefully, there you go. So hopefully, as you can see, actually some of them, what's more interesting is the number of people who say they're really not sure. That's not surprising. That's not a bad thing. This is something which has not really been discussed a lot within the industry and has not been discussed really down at the plant level, at the reliability, robustness level within an organization. Everybody's focused on their KPIs and on how much their automation system is staying up or producing, really without worrying too much about, okay, what happens if it goes wrong? And it's very encouraging to see at least 10 people have a very robust system. That's very encouraging. All right, so we'd like to move on as a result of that and say, okay, even if you do end up with a really, really robust system that you can withstand different things getting on the networks, different configurations, things going wrong, what we hear a lot about is the advent of smart systems. Everything is moving to being smart in the industry, from being smart grids, smart meters, smart cities, smart factories, smart automation, smart cars, you name it, everything is going smart. And really what that's talking about is saying we're going to use data at the edge to pull back in to make decisions at machine speed at the core, and making those decisions at the core, we're then going to push out instructions back to the edge to manipulate a system. So if you think of within a power industry, this is called demand response. How much people are using at the edge should drive how much you actually start producing at the core and where you send the electricity in the grid, and where you can how much electricity should be cheap, etc. And you start making decisions based on all the information at the edge, and then you start pushing out control information from the core back to the edge. Well, that all relies, smart systems inherently rely on the accuracy and the authenticity of that data. That's to say that machines that are making decisions in real time based on that data when it could very well be a dumb system, i.e. if I'm an attacker on a network and I just manipulate the data, so it's still a reading coming back from the edge, I just start changing the data in that message. Well, that's going to mean that the decisions made at the core are going to be made on faulty information, and actually it's not going to be clever responses coming back, it's going to be dumb responses. And that's actually very, very common with industrial control systems. Why? Because as we said before, the integrity protection within many industrial control system protocols is really about has noise affected the signal? Has the message been manipulated by the environment as we go through it? Not has the message been intentionally manipulated by an attacker. If you imagine in many of these industrial control protocols, you can imagine them essentially as being a whole load of postcards where a control will write out a postcard, write what their values are in them, on the postcard, and then put it into the post, giving any opportunity for an attacker in any position from the mail sorting room to the postman has the ability to take out that postcard, to erase the information contained in it, and to put in its own information and continue delivering the letter. Integrity protection is just not there. There may be some good CRC codes, checksums to make sure noise hasn't been interfered with the packet, but there's no way to validate that the information you've said is actually what's been received. And this happens in quite a lot of examples, and it doesn't need to be destructive. So we have at the top right there Stuxnet. Everybody knows really what happened there, where once malware got onto a workstation engineering terminal, it manipulated the program, and then that was pushed down into the PLC, such that the readings coming out of the PLC and was being displayed on the HMI to the user, what the speed of the centrifuges were spinning at as being displayed to the user is not the speed that was actually being spun by the centrifuges out at the edge. The information was being manipulated. And that caused destruction, that caused interference with the process, but it doesn't have to be even destructive. One of my favorite examples of this was in Puerto Rico, where about 5 years ago, somebody managed to hack into their smart meters and work out how it can actually reset that smart meter back to 0 at the end of every month. So it looked as if he could run his air conditioning unit the whole day, every day, and at the end of the month just dial it back, and he was charged for no electricity. What was surprising was no destruction, nothing manipulated, just the information coming from the edge back to the core. Once they worked this out and he started to tell his friends and more people started doing this, the company in Puerto Rico realized that, oops, if this had continued, they would have lost about $400 million in 1 year alone from lost electricity usage. That's how bad it was. Why? Because there was no validation, no integrity protection to validate the information coming from the edge is actually true. And you may say, okay, but how easy is it to really manipulate that information? What we've shown on the bottom is just a wide variety of different uses. As I like to say in the security community, hardware hacking is the new software hacking. We're used to malware, we're used to attacks being perceived as coming from pieces of software. And my industrial control system is air-gapped, so there's no way for that software, no way for that information to come from the outside world, from the internet, onto my system. Well, with the advent of these small little cheap computers, such as the Raspberry Pi bottom left, has actually made it really easy for me to bring my malware, bring my attack into your network without it being over an internet connection. I'll bring the internet to you, because I can take that Raspberry Pi and I can start putting it into anything. If you see there's a power strip, that big bit at the end of the power strip, that actually contains a cell phone and a Raspberry Pi. So if you check under your desk and you check to make sure that that power strip is, you have your laptop, you have your display, you have your printer plugged in there, but does that power strip also have an Ethernet connection, and is that plugged into your network as well? I mean, how many people check this? But then again, Stephen Hilt at S4 actually showed I could do the same thing, but for a PLC and RTU. So what he did was he pulled out the innards from a I/O module of an RTU and put in a Raspberry Pi and a cell phone in there and snapped the cover on the front. Nobody had any idea that wasn't a real module. Now he has direct connectivity into the backplate, into the control system itself, right at layer 1, layer 0. So he was able to, via the cell phone, he can now dial in and inject whatever commands he wants. He has worldwide connectivity into an air-gapped network. And in the bottom right there, we show exactly what a team of researchers now started to do in light of the Edward Snowden leaks. They said, you know what, we can actually manufacture some of the similar tools that was leaked to the press, including there's a wireless receiver there in the USB cable. So that small little USB chip on the bottom right actually contains a radio receiver as well. So not just physical units, but small little USB or Ethernet cables. How many people check their Ethernet cables? Now we have to realize that we live in a world where we can have radio connectivity. We can have a malicious Ethernet cable. And at that point, you can now start manipulating data. You can now start manipulating events on a real, in your control network, even if it is air-gapped. So these are some examples where people haven't really put a lot of protection into that, haven't sort of taken active steps to even do integrity protection. I'd like to ask Adam to briefly describe a little bit more about the OSGP and what happens when people intentionally try and solve this problem.
So as Alex mentioned with Stuxnet and the Puerto Rico meter example, a lot of protocols kind of lack these cryptographic integrity checks where you can ensure that what is said is actually what is heard. But there are efforts by proprietary vendors and standards bodies to actually engineer security into industrial protocols. But there also have been some kind of missteps along the way. Open Smart Grid Protocol is an example from this past May where I think it was a team of European researchers analyzed the standard and the digest function on every message that is supposed to prove the identity of the sender, and found that they could fairly trivially recover the private keys used for either side of the connection. And this is mostly just a result from the fact that the standards body had used a kind of homegrown cryptographic function to try to protect the payload. Engineering cryptographic protocols is a very subtle endeavor. Even the best people get it wrong. It takes a lot of vetting from a lot of people and a lot of people looking at it from an adversarial mindset. And I've started to see this a little bit with standards in electric power where we're now adding in security into protocols that are 15, 20 years old, and probably not enough is being done to actually vet these work from people kind of outside the community. So just because the vendor says we have security, or even if it's a standard, I think we need to start challenging assumptions about how secure that is. Because having a system where you believe that you actually have endpoint security and you don't, and you've invested a lot of money in it, and perhaps not put as many compensating controls in place because of that, is a really dangerous situation. So I'll turn it back over to Alex now.
Thank you, Adam. So as we said, there's really two differences here with the SMART system and two different approaches, one of which is we're going to put something in place, we're going to actually test it, and we're going to make sure that it is robust, and we're going to have other people start looking at it. Or there's the approach of basically saying, we've done it, we think it's good, you should just trust us. So again, time for everybody to wake up a little bit. We've now sort of asked you, is your industrial control system robust? Now we really want to know, is your control system smart? And more specifically, how do you know it's smart? Do you know it's smart because you've actually tested, you've had people come in and try and manipulate stuff and see what happens? Has it been independently validated? Or do you say, yeah, it's smart because I bought the latest system and they told me it was smart because it had smart in the name? Or do you actually just not know? Or do you not really care about your industrial control system being smart? So again, we'll ask everybody to fill in their answers, and we'll give you a bit of time to do that. Okay, so hopefully we've managed to keep people awake. So we'll probably just close the poll here. And again, it gives us about 30 seconds to compile the results, pull it all together. We hope nobody's been manipulating the data on the way, and we'll provide you the results shortly. Okay, so we got our results in. And again, it's surprising. So we actually have less people who have got they've actually gone out and tested their system. So even though they can have a robust network, not necessarily going to have it, tested and made sure that their industrial control systems is secure. So the reason why we brought this together, the reason why we're talking both about robustness and smartness is because that's really what makes a resilient system. And when I say resilience, I don't really mean availability. Why? And this is what we coming back to the very beginning when I said availability is paramount, but it can actually hurt you. Because availability without resilience, what it actually means is my ability to crash a system at will. This is something we've definitely seen within DNP3, and what Adam's discovered is the drive for high availability means that as an attacker, I can guarantee that my poison packet, my malicious event is going to be received where I need it to be received. I can rely on the high availability of the system to get my bad information where it needs to go. So that's one issue where resilience is not the same as availability. What is resilience then? Well, resilience is really restricting a system to only do what you want it to do. And this is surprisingly difficult. You can design the system to do what you want it to do, but to actually make sure that that's the only things it does is actually very, very difficult. I mean, I threw up there an aviation security example, just saying, you know, I only want to have good things on my aircraft. Well, the TSA, the DHS approach is to basically have a blacklist. They say, all right, well, you need to look for what is disallowed. We're going to have a long list of things that aren't allowed. Well, actually what that means is that's incredibly resource intensive. That's incredibly heavy. And every time a new attack comes out, they have to add another thing to that list and continue to look for yet another thing. Why? Because they haven't designed their system to be resilient. They haven't designed it to only allow through what is authorized. Instead, what they're trying to do is detect what is unauthorized and try and push them out. So in reality, it's easier to try and restrict to only what is good rather than trying to pick out what is bad. And early detection response is a great way of validating that you have good things, is a good way of ensuring that your security is working. So that if a bad event does occur, even if it's not going to actually impact your system, you alert, you say, hey, I have something occurring on my network which shouldn't be occurring. Then you can try and find the source of that breach, the source of that event, without worrying that it's actually impacting your system. But you get an early warning system that somebody's trying to do something they shouldn't do. And that really comes down to quality control and testing. Without that, you can't be assured that what your system is doing is what it should be doing. And as we say, resilience ultimately increases security. And security increases resilience. They're essentially two sides of the same coin. By building a system to only do what I want it to do, means that if I'm an attacker and I get in, the only thing I'm allowed to do are authorized actions, are safe actions. So again, I can be disruptive, but I can't be damaging. And I think that's one of the key points here that sometimes gets missed. And it ties in exactly with zero-day vulnerabilities. Everybody's worried, oh my God, what happens if my PLC is revealed to have a zero-day vulnerability? ICS cert, it seems like every day, if not every week, we see another vulnerability, another denial of service, buffer overflow, bad static credentials in a control system, and we have to go out, we have to patch, we have to try and fix it. Before we have patched our system, we are operating at risk. We have a real concern. Well, if we build resilient systems, then what we can say is, you know what, even if the vulnerability exists, but an attacker is unable to exploit it, is it really a risk? I mean, one example of that is if we know that a malformed DNP3 packet could crash my system, but I only allow well-formed DNP3 packets, well then, because an attacker isn't able to send a malformed packet, isn't able to actually cause my machine to crash because I'm not allowing him to say anything bad. This is one of the key differences, and this is one of the key things to make a system secure and reliable and resilient. So, in reality, how do we do this? Well, if you think about it from an IT perspective, the difference between IT and OT, in the past, we've traditionally relied on boundary protections. That is, we want to keep bad things out. If we keep bad things out, bad people out, bad actions out, then we can say that basically we've designed our systems to only operate good, well, then we should be okay. But in reality, we've moved on from there. We just know that there's too many ways in which bad things can get in, be that a USB stick, be that a PDF, be that even malformed firmware. We've seen recently, along with the Havex attack on OPC, we've seen again the Energetic Bear campaign target industrial control manufacturers and actually infect their vendor's firmware. So when if you go to a vendor's website to download the latest firmware, you're actually downloading a malware-infected piece of firmware, and you yourself will install it into your own network. So there's just too many different ways in which bad things can get in and disrupt your industrial control system. And this is where we've come to this realization. We said, you know what, even though my PC in my enterprise may sit behind a firewall, I'm still going to put antivirus on it. We wouldn't assume, we would never consider keeping our PCs on our networks, on the network, connected to anything without having antivirus on there. And we have configuration management, and we enforce policies for what a user can do. We have all of these endpoint protections and limitations, trying to make the PC as resilient as possible. But in the post-Stuxnet world, we've basically done the same thing. We try and limit actions of what somebody's allowed to do on their PCs. But what about all the RTUs? What about all the controllers? What about everything on my control network that isn't a PC? Where is the same level of protection? If you think about your control network, you say, don't worry, all my controllers, all my PLCs sit behind a firewall. Well, the same PCs that sit behind the firewall that talk to controllers, are you running antivirus on the PC? If you are, it's because you think that there is a risk that malware could get in, a bad action could get in and target my PC. But if that's the case, then your endpoints, your PLCs and your RTUs are vulnerable to the same types of attack. It's just that attackers are now going to start focusing on the unprotected things. You basically, by adding all the endpoint protection to your PCs, you're driving the security researchers, you're driving the hackers, the attackers, to your unprotected side. And those are the devices that are actually interacting with the real world. Those are the ones that are in the most desperate need of protection. So how do you go about actually taking the IT side and actually start applying it to your the OT side? We have great standards like ISO 27000, you have the NIST 800 series, FISMA. You have a lot of approaches for how you can actually protect an enterprise network, but not a lot of standards or approaches for how you're going to take that and apply it to industrial control domain. Specifically, how do you do that and maintain high reliability? In an IT sense, when you have an attack, one of the first things you want to do is quarantine your system. You want to basically stop the attack from spreading. You can unplug devices. When attackers started to hit Saudi Aramco, they immediately started running around unplugging Ethernet cables from machines, turning off power, stopping the spread of malicious malware. Well, that's very difficult to do if you're on an aircraft flying at 35,000 feet, or you're on a train, or you're on in a nuclear power plant. You can't just start unplugging everything and turning everything off instantly. You have to still maintain a safe operation. So what applies in the ISO world doesn't necessarily apply in the IEC or ISA world. So this is exactly why the team at group at ISA started up a standard called ISA 99 that has subsequently been adopted by IEC into an international standard called IEC 62443. And what this really is the first big attempt to create a comprehensive set of standards that apply specifically to the industrial control domain. This is not an IT standard, this is an OT standard. And really what they talk about is basically, in their good, a little standards terminology heavy here, but it's about preventing illegal or unwanted actions. And they do this by what they call their zone and conduit model. That is, segment their networks, stop all non-essential communications, and make sure that everything is operated according to a risk assessment process. Well, you can go out and you can read all of those 13 different standards, the collection. You can read it, you can try to understand what it says, but in essence, it basically says this: control who can talk, control who they can talk to, control what they can say, and monitor and alert in the event of infractions. That's basically what it comes down to. Now, how much control you do and how you segment everything, that's really according to a risk assessment, risk management process. What we mean by that is, we take, and on the right-hand side is an example of an IEC conformant domain industrial control system. But that's where they've divided up all of their parts of their networks into zones. If you notice, there's not really any flat zones. Everything is divided up into areas where they have common security requirements and areas of sort of equal impact. Because if you imagine, if we're controlling what can come in and out, like you have a wall around a city, once an attacker gets in, they can do whatever they want inside a network, but they can't jump between networks. They can't jump between zones. The whole concept of this is you group assets together, control which zones can talk to which zones, and you monitor and protect those zone-to-zone communications. And you don't necessarily do that by just using one type of technology, because one type of technology or security might not meet the operational requirements of your network. You can't potentially put a specific piece of technology in which impacts the latency of communications through your network. So you might have to mitigate it in other methods. And again, it does advocate multi-vendor security. You shouldn't really have the main automation contractor who put in the safety system, who put in the entire system, also be the security vendor. Why? Because there's not the incentive there. The incentive security is to make sure you can't break it. The incentive of the MAC is to make sure that it's incredibly reliable. And the two may not be in common cause. So actually, sometimes multi-vendor security is a very good approach to do, where you have competing requirements that ultimately require everybody to work together to solve it in a common way. So what are some of the specific recommendations? If you go and read 62443-3-1, it has some really good advice in there for how you go about implementing different technologies. But as they well acknowledge, not all the technologies are universally available. For instance, they really like the adoption of authentication with authorization. But they do acknowledge that protocols, as we've talked about previously, the protocols in the ICS world don't generally have any of this network authentication, don't have any integrity protection. There's no way to do that. Same thing with host-based firewalls. We put firewalls, we have Windows firewall built in, we have network firewalls, but we don't have any host-based firewalls for our PLCs. So we have to rely on everybody else and hope that all the other systems are intact in order to protect our industrial control endpoints. Same thing with encryption and data validation. Encryption is a good thing, and not because of confidentiality. Encryption is a good thing because it provides authenticity. You know who sent the data because you can cryptographically prove who sent the data, and you can also cryptographically prove that that data hasn't been manipulated. It's integrity and authentication. It's not confidentiality. But as we described previously when it comes to the Open Smart Grid Protocol, just because you've done encryption doesn't mean you've done it right. It's surprisingly difficult to get encryption right, which is why you want to do something that's been independently validated, independently proved to be secure and the right implementation. So they advise, if you're going to use encryption, make sure that the systems and the protocols have gone through an independent validation scheme such as FIPS 140-2. It's a universal standard. It's quite heavily used here in the States, but it has applications throughout the whole world. The idea being we can validate that what you've done has built upon what we know to be good. If you start rolling your own encryption, if you start relying on proprietary encryption, you're going to have a bad time. That's just the fundamental truth of it. And then finally, the management, audit, measurement. Basically, we need to do intrusion detection, we need to do monitoring, and we need to do alerting. But the reality is, while that stuff may exist for enterprise systems, it doesn't really exist for industrial control environments, PLCs are to use, nor does it really understand the protocols being communicated. And we can all buy good industrial firewalls that limit who can talk to whom, but they don't really understand what's being said. And even if the firewall does come with great intrusion detection systems, in reality, it's pretty much going to be signature-based. And what we mean by that is, again, it's like the aviation security approach. They've written certain signatures, certain blacklisted items into it, and they have to identify every single instance of the blacklist. Instead of taking a different approach, which is being protocol aware, being actually understanding what is being said and making sure it's well-formed and only allowing good actions, the whitelist approach. I actually don't need to know too much. I don't need to have any signatures of known malware if I don't allow malware in. If a malware can only communicate legitimate, good pieces of information, then I don't need to have a blacklist approach to actually drop out malformed packets. So that's exactly, and this is the one little selling slide we put in here, and that is the EtherWatch, the cyber defense devices that 3TI produced was exactly in response to these concerns. These are deployed quite widely within oil and gas and within the U.S. military, DoD environment, because they wanted to have exactly those things advocated to by IEC 62443. They needed within their control environment to control who's allowed to talk to their controllers, and they wanted to make sure they couldn't rely on the signatures, which are sort of previous generation technology to identify everything that's bad, especially in this constantly changing environment that is industrial cybersecurity. They really wanted a whitelist approach which said, look, I only want to allow authorized actions. If I know that things should only, my controller and my server are only going to exchange a few types of messages, I want to make sure that those are the only type of messages that are allowed to be sent. So that's ultimately what we put in there. And we included FIPS validation, validated encryption to provide integrity protection. And so we have a full protocol parser that understands everything from DNP3 to Modbus, OPC, Ethernet IP, CAN bus and CAN open, and we even bring out BACnet and FOX protocol parsers in the very near future. So in reality, at the end of this whole talk, and hopefully you've managed to bear with us throughout all of this, if I could leave you a couple pieces of advice, it would be this. Do not use flat networks, even at the control layer. This is what Target did. They had an incredibly flat network where everything talked on the same network. The problem is once an attacker got in, they could compromise everything. You now just have one giant impact zone. Don't use flat networks. Segment off the networks as much as possible. Protect integrity. It's not confidentiality, it's integrity and authenticity, which means encrypt the conduit links. Encryption's got a bad rap within industrial control systems because they say, you know, it impacts latency, we don't have enough speed, you can't do that. In reality, encryption's come a long way, especially hardware encryption. We found, encryption does not impact normal operations. In fact, it benefits them. So encrypted conduit links actually are a great way to minimize anybody connecting into your network and communicating when they shouldn't be. If it's not encrypted, it's going to be dropped. It's a great filter mechanism, as well as providing authenticity and integrity protection. Filter communications. And what we mean by that is just because you're connected to the network and just because you can talk to everybody doesn't mean you actually should be talking to everybody. Not every PLC should be able to talk to every PC or even any other PLC. If a PLC is only talking to one server, then we need to limit that communication so that that PLC can only talk to that PC, that server, and vice versa. We limit who's allowed to talk to whom. In case malware does get on there, it means that they can't, again, disrupt the process. They can't do anything bad. If the computer is only allowed to talk to a few specified endpoints, then the malware is only allowed to communicate to those specified endpoints. And again, filter communications by known protocols. Make sure that the only thing being allowed to be communicated between those endpoints is what you intended it to be. Inspect and parse communications. This means to make it resilient, you need to make sure that the only things you're allowed are well-formed packets, well-formed communications. This is exactly what Adam was describing. What he found quite heavily within DNP3 was a malformed packet or a poison packet can crash an industrial control system. It's very easy by sending a malformed packet, which is still the correct protocol, still between authorized endpoints, it will crash a system. We can't have that fragility in our network. So we only allow well-formed communications, and they need to be appropriate. Just because you can reprogram a controller over the network, we can reprogram a controller's firmware, doesn't mean we should do that during normal operations. Once you have your system set up correctly, what you want to do is say, you know what, this message, while it is a legitimate and well-formed message, isn't actually appropriate for this time, or maybe not appropriate for that number of frequency. Should I really be telling it to switch set points? Should I really be asking to read its value every millisecond, or every 10 seconds, or every minute? We need to understand how often that command is coming through, as well as when it's coming through. And finally, monitor activity. You shouldn't just rely on monitor between one domain and the next domain. We actually need to monitor all communications and look for trends, look for those anomalies. And finally, test. If I could leave it with one thing, it's definitely test, test, test. Do not rely on other people. There are definitely the vendors. We're a vendor community. We're part of the vendor community. Don't necessarily believe us. Don't rely on us to tell you the truth. Have it independently validated. There are lots of different schemes out there, lots of different companies who can help you do this. And if I leave you with one little quote by a famous IT person, Eugene Spafford, it's a system is secure when it does exactly what it's supposed to do and nothing else. If we can get this, then we'll end up with a resilient system that's both smart and robust. And finally, a shout out to the ISA Process Control and Safety Symposium. It's a great conference, and now seeing that security is a part of safety, is a part of security process control, we'll be speaking at it, and we highly recommend everybody comes to that. So thank you very much. We've kind of reached the end of the presentation. We'll now open it up to question and answers. So feel free to submit questions in the chat window. We'll have those pop up, and we'll be back with some of the answers. Thank you very much. Okay, thank you for waiting. So we have one of our first questions is, will encryption protect my system from malformed packets? This is the idea that if we just put encryption in the way between my endpoints, I should be able to control and prevent malformed packets. Unfortunately, that's not necessarily the case. Encryption will just ensure that what is being sent is what is received. So a malformed packet will be encrypted just as well as a well-formed packet. Encryption does a great job of keeping bad guys outside. It does nothing to prevent attackers inside from doing anything. So it's just a tunnel. Encryption is just a tunnel. Keeps everybody outside the tunnel from getting in, but anybody inside the tunnel can go either way. So one of the questions is, most of the software systems ask us to exclude some files from antivirus scan. How can we tackle this while implementing security? This is a great question. This goes to the heart of what we call of the resilience. We've basically said that putting antivirus onto a system can really impact the resilience, the robustness of my network, because it could start classifying good files, good things as bad. And as soon as you start getting rid of good files, you start impacting the ability for that file system, that program to actually do its job. And the reality is because antivirus, as we mentioned before, is really a blacklist approach. It's trying its hardest to identify all the different known sets of malware, when in reality, that's a very difficult job, and you're always going to be playing catch-up, and it's always going to be misidentifying packets. There are a couple of good schemes out there to instead of providing antivirus, which is essentially a blacklist, to actually do whitelisting approach. So you don't need antivirus. Instead, what you say is, I'm only going to allow good and known good files to be implemented. So I think there's a group, including Billy Rios, has started up an independent organization to start trying to provide a list of a hashed list of known good programs. So for the industrial control environment, so you can actually start implementing a whitelist approach to what's running on your PC instead of relying on antivirus, which is a blacklist approach. Another question we have in here is, do you have an opinion on the use of port blockers for keeping portable devices from being connected? This is a great question, and I like it. We're always in favor of different technologies to help mitigate problems. And the real problem with USB ports is the fact that anybody with the inclination can plug a USB stick into it. And that, as we mentioned before, it doesn't necessarily have to be nefarious. It could just be because they want to do something legitimate. They either have a concern they don't know whose USB stick it is, so they're plugging it in order to find out whose USB stick it is, or it's because they're trying to load on a new user manual or upload firmware, or collect information from one computer and transfer it to another computer. These are all legitimate actions, and you're never going to defeat human behavior. No matter how many times you tell them don't plug a USB stick in, there's always going to be a driving need to do it. So the port blockers just mitigates that issue, just takes it away and say, you know what, they can't do that. The one issue with that, and I advise you to all go out and have a look at what we call the USB rubber ducky. And the idea there is we block the use of USB sticks, memory sticks, but we don't necessarily block the use of USB keyboards or USB mice. Why? Because they're the most prevalent form of being able to submit information into our computers. But what we can do is, with the USB rubber ducky, what you can do is you can actually take control of a USB keyboard and you can start typing in your own malware. So if you type on your own computer the Windows key and R, and then type the words PowerShell and return, it will pop up a whole little terminal window in which you can start executing commands. So this is one example where a port blocker or preventing the use of USB sticks doesn't necessarily prevent the attack entirely. It just helps mitigate user behavior, accidental user behavior. Okay, so we've got a whole load of questions in here, and I really appreciate the questions coming in. Unfortunately, we started to run out of time. So what we'd like to do is take the opportunity to respond to you offline with answers to those questions. And we greatly appreciate you attending our webinar and look forward to seeing you at the ISA Process Control and Safety Symposium in Houston. Thank you very much.